Hello my friends and welcome back to the FooTech HD channel. Open die forging is a metalworking process where a metal billet is shaped between multiple dies that do not enclose the material entirely. This technique, also known as Smith forging, allows for the creation of large, simple-shaped components with improved mechanical properties due to the reduction in porosity and refinement of the grain structure. One key advantage of open die forging is its ability to produce parts with exceptional strength and durability. This is achieved by applying repetitive compressive forces to the metal, typically heated to temperatures between 1000 and 1250 degrees Celsius, 1832 to 2282 degrees Fahrenheit, to gradually shape it. The process relies heavily on skilled operators and large machinery, such as hydraulic presses and hammers. These machines can exert enormous pressures, ranging from 500 tons to over 6,000 tons, depending on the size and complexity of the part being forged. The open die forging process can produce components weighing up to 200,000 pounds, approximately 90,718 kilograms, and with lengths exceeding 80 feet, about 24 meters. Commonly forged materials include carbon steel, alloy steel, stainless steel, titanium, and nickel alloys, selected based on the intended application's requirements. This method is highly versatile, capable of creating a wide range of products, including shafts, flanges, hubs, and rings. For example, crankshafts forged through this process can weigh as much as 65,000 pounds, around 29,484 kilograms, and measure up to 36 feet, approximately 11 meters, in length. Similarly, forged rings used in aerospace and industrial applications can have diameters exceeding 30 feet, about 9 meters. Open die forging offers several benefits, including improved mechanical properties, superior structural integrity, and the ability to produce very large parts. Despite its slower production rates and higher costs compared to closed die forging, it remains a crucial technique for industries requiring large, high-strength components. The Radial-Axial ring rolling machine is an advanced piece of machinery designed to forge rings with high precision and efficiency. Operating on the principle of applying both radial and axial forces, it shapes the material into rings with excellent control over the final product's dimensions and properties. Key components of this machine include the main rolling mill, a hydraulic system, a control system, a heating furnace, and automated loading and unloading mechanisms. The process begins with heating the workpiece, usually a preformed ring or blank, in the heating furnace to reach the desired forging temperature. This temperature is crucial as it makes the material malleable and easier to shape. Once the material reaches the appropriate temperature, it is automatically loaded into the main rolling mill. The loading mechanism ensures the workpiece is correctly positioned for the rolling process, initiating the radial rolling stage. During radial rolling, the radial roll moves towards the workpiece, applying pressure to its outer diameter. This pressure reduces the thickness of the ring while increasing its diameter. The computer control system monitors the rolling force and adjusts it as needed to maintain uniformity and precision. Simultaneously, the axial rolls apply force to the side faces of the ring, controlling its height. This ensures that the ring maintains the desired axial dimensions while the diameter increases. The coordination between the radial and axial rolls is critical for achieving the required ring geometry. Throughout the rolling process, the control system continuously monitors various parameters such as rolling force, temperature, and material deformation. It makes real-time adjustments to the rolling speed and force to ensure consistent product quality and adherence to specifications. After the ring reaches the desired dimensions, it is automatically unloaded from the rolling mill. The unloading mechanism ensures that the hot ring is safely removed and transported for further processing or cooling. The radial-axial ring rolling machine offers several advantages. Its advanced control system allows for precise adjustments during the rolling process, resulting in high-quality rings with tight dimensional tolerances. The machine's versatility is evident in its ability to handle a wide range of materials, including carbon steels, stainless steels, nickel-based alloys, and titanium alloys, making it suitable for various industrial applications. The rolling process ensures a fine grain structure and excellent material properties throughout the entire cross-section of the ring, enhancing its mechanical performance. Energy efficiency is another notable benefit. The machine's design allows for forging in a single heat, reducing energy consumption and increasing productivity. Additionally, it offers flexibility in production, suitable for both large batch and unit production, with minimal downtime when switching between different ring sizes and materials. The integrated plant concept allows the radial-axial ring rolling machine to be part of a complete forging line, including heating, loading, rolling, unloading, and control systems, providing a streamlined and efficient production process. The V1200, a Russian-designed pressurized water reactor, represents the forefront of nuclear power technology. Its construction embodies sophisticated engineering and meticulous craftsmanship, ensuring a safe and efficient energy generation system. Central to the V1200 is its reactor vessel, a critical component designed to withstand extreme conditions and ensure the reactor's integrity over its service lifetime of 60 years. Material and manufacturing. The V1200 reactor vessel is constructed from pearlitic steel, specifically the 15X2 HMOA grade. This material is chosen for its high strength and resistance to radiation-induced degradation. The manufacturing process begins with smelting and forging, producing ingots weighing up to 360 tons. These ingots are then processed using a press with a power of up to 15,000 tons force, ensuring the material's integrity and strength. Nozzle shell rings. The nozzle shell rings are among the most complex and essential parts of the reactor vessel. Each ring is integrated with multiple nozzles, including coolant inlet and outlet nozzles, which facilitate the circulation of the coolant necessary for maintaining optimal reactor temperatures. Additionally, the rings feature 5 emergency core cooling system (ECS) nozzles, 1 of 850 mm diameter and 4 of 300 mm diameter. These nozzles are critical for injecting coolant into the reactor in emergency situations, preventing overheating and potential core damage. Support shell ring. The third ring, the support shell ring, plays a pivotal role in the overall stability of the reactor structure. It includes a specially designed rim that supports the entire reactor assembly. This structural support is crucial, given the reactor vessel's substantial weight of 334 tons and its extensive height of 12 meters. Central shell ring. The central shell ring is subject to significant neutron irradiation throughout the reactor's operational life. Its exposure to high levels of radiation makes it a critical factor in determining the reactor's lifespan. The engineering and material choice for this ring are therefore of paramount importance, as they directly impact the vessel's durability and safety. Lower shell ring and bottom head. The lower shell ring and bottom head are integral to the reactor vessel's functionality. The elliptical bottom head is designed to support structures that hold the core fuel assemblies at precise distances. This precise placement is essential for maintaining the reactor's efficiency and safety. The lower shell ring, along with the bottom head, must endure extreme conditions, making their design and material composition critical for long-term operation. Heat treatment and hydraulic pressure tests. Heat treatment is performed at around 650 degrees Celsius to relieve stresses and enhance the material properties of the reactor vessel. This is followed by rigorous hydraulic pressure tests to verify the integrity of the pressurized equipment. The testing procedure involves filling the reactor with water, generating test pressure, and carefully reading instruments to detect any potential leaks or metal ruptures. The reactor vessel must withstand pressures ranging from 254 to 304 atmospheres without any detected leakages or ruptures, ensuring its reliability under operational conditions. Operational specifications. The V1200 reactor vessel is designed to handle an outlet reactor coolant temperature of 328.9 degrees Celsius. This high operational temperature is essential for efficient energy production, requiring the vessel to maintain its integrity under extreme thermal conditions. The vessel's large dimensions, 4.5 meters in diameter and 12 meters in height, coupled with its weight of 334 tons, underscore the engineering challenges involved in its construction. The ITER, International Thermonuclear Experimental Reactor, project represents a monumental step forward in the quest for sustainable and clean energy through nuclear fusion. Central to the construction of the ITER tokamak, a device designed to harness the power of fusion, is the manufacturing of the vacuum vessel, VV. This component is a crucial element that forms the heart of the reactor, housing the superheated plasma in which fusion reactions occur. The procurement and assembly of the ITER vacuum vessel are shared between Europe and Korea, with Europe responsible for 5 sectors and Korea for 4. Manufacturing milestones in Korea. Hyundai Heavy Industries, HHI, in Ulsan, Korea, has made significant strides in producing these complex structures. The company recently finalized the first of the 9 vacuum vessel sectors required for the ITER tokamak. As of now, Korea has completed 3 of these 40-degree sectors, with a 4th sector nearing completion at over 90%. The manufacturing journey for each sector is a testament to advanced engineering and meticulous quality control, given the stringent requirements and challenges involved. Each sector of the vacuum vessel weighs approximately 440 tons. These massive structures undergo rigorous manufacturing processes, including cutting, welding, and assembly, before being encased in protective housing and prepared for shipment. The completed sectors are transported via a combination of boat, barge, and road to the ITER site, where they undergo site acceptance testing and pre-assembly activities before being installed in the tokamak pit. Key manufacturing challenges. The production of the ITER vacuum vessel sectors is a first of its kind, FOAK, endeavor, presenting several unique challenges. 3 main hurdles are particularly noteworthy. Nuclear safety process. The vacuum vessel must comply with French nuclear pressure vessel standards, necessitating rigorous approval of all applicable documents by the Korea Domestic Agency, KODA, the ITER organization, EO, and the agreed notified body, ANB. This process involves multiple qualifications, demonstrations, and certifications to ensure adherence to essential nuclear safety requirements. Maintaining traceability for all activities is crucial, with each manufacturing step inspected and recorded by resident inspectors from the Vacuum Vessel Project Team, VVPT, and A&B. Volumetric examinations. Ensuring the integrity of the double-walled, fully welded structure with its complex 3D geometry requires 100% volumetric inspections. For Sector Number 6 alone, the HHI team executed approximately 995 meters of full penetration welds, supported by 20 welding procedure specifications and 60 specialized scanning techniques using phased array ultrasonic testing, PAUT. Tight tolerance requirements. Achieving the precise dimensions required for the final assembly of the D-shaped vacuum vessel is particularly challenging due to the heavy, double-walled segments and their inherent deformations during manufacturing. To address this, the HHI team collaborated with VVPT to perform virtual fittings using actual dimensional data, defining target positions for each fiducial post on the poloidal segments, PS, before commencing the final assembly. Quality assurance and testing. Quality assurance for the vacuum vessel sectors is paramount, given their critical role in the ITER reactor. Each manufacturing activity is controlled through a manufacturing inspection plan, MIP, documenting all processes and ensuring adherence to quality control measures. During the production of Sector Number 6, 45,000 inspection points were executed, and 500 manufacturing documents, including reports, were developed. A crucial part of the final acceptance testing for the vacuum vessel sectors is the helium leak test, ensuring the vacuum performance meets stringent safety standards. Initially, a 200 degrees Celsius baking process was considered essential to achieve a low background leak rate. However, given the risks associated with baking, the decision was made to perform the leak test without it. Instead, pre-pumping the VV interspace demonstrated that the background leak rate and total pressure were sufficiently low to conduct the test. The successful helium leak test on April 5, 2020, confirmed the sector's integrity, with a calculated leak rate of 6.08 times 10 to the -9 pascals bullet operator M³ bullet operator S⁻⁻1, well within the acceptance criterion. Logistics and transportation. Transportation of the vacuum vessel sectors is another complex aspect, classified as a protection important activity, PIA, under French nuclear regulations. The detailed transportation plan, including quality and inspection plans, must be approved by VVPT and A&B before implementation. After successful sea transport, Sector Number 6 was unloaded in Fos, France, on July 22, 2020, and delivered to the ITER site on August 7, 2020. Unpacking and site acceptance tests, including another helium leak test, are conducted at the ITER Assembly Hall, following a meticulous assembly schedule. The manufacturing process of a flange begins with steel billets, which are long bars of steel that serve as the raw material. These billets are cut into smaller. The cut billets are then heated in a furnace to a high temperature, making them malleable for forging. In the hammer forging process, the heated billet is placed on a forging die and repeatedly struck by a power hammer. This process shapes the billet into the rough shape of the flange. After hammer forging, the flange undergoes punching, where a hole is created in the center. Next, the roughly shaped flange is subjected to rolled forging to achieve its final shape. The piece is heated again and placed between two rotating rolls, one fixed and one adjustable. As the rolls rotate, the billet is compressed and elongated, forming a ring shape. This process refines the dimensions and improves the grain structure of the metal, enhancing its strength and durability. Rolled forging is especially important for ensuring that the flange has a uniform cross-section and meets the required specifications. The final stage of flange manufacturing involves machining, which includes precise operations like turning, milling, drilling, and finishing. In the machining process, the forged flange is mounted on a lathe or milling machine where it undergoes turning to achieve the required outer diameter and surface finish. Milling may be used to create any necessary flat surfaces or additional features. Drilling is a critical step where bolt holes are created around the flange's perimeter. These holes must be accurately placed and sized to ensure proper fitment with mating components. The flange may also undergo threading if needed for specific applications. Finally, the flange is finished through processes like deburring, polishing, and coating to enhance its appearance and resistance to corrosion. Quality control checks are performed at each stage to ensure the flange meets the required standards and specifications. Gear forging is a manufacturing process where metal is shaped under high pressure to create gears. This process typically involves heating the metal to make it more malleable, then using dies to form the gear's shape. Forging produces gears that are stronger and more durable compared to those made by casting or machining. The grain structure of the metal is aligned during forging, enhancing the gear's mechanical properties, such as toughness and resistance to impact and wear. Two common methods in gear forging are open die forging, which is suitable for large gears, and closed die forging, which is used for smaller, more precise gears. The precision and strength of forged gears make them ideal for high-stress applications, such as in automotive transmissions, aerospace components, and heavy machinery. Additionally, the forging process can reduce material waste and machining time, leading to cost savings in large-scale production. The 13,000-ton forging press from Doosan Heavy Industries, manufactured by SMS Mir in September 1982, is a monumental piece of engineering designed for open die forging. This press, a 4-column pushdown type, operates using water hydraulics, which offers advantages in terms of power and precision. With an impressive capacity of 13 meganewtons, 13,000 tons, this press is capable of handling some of the most demanding forging tasks, making it essential for industries requiring large and complex metal components. The maximum press stroke is 4,500 millimeters, allowing for significant deformation of workpieces in a single operation. This large stroke capacity is crucial for producing long or thick forgings without the need for multiple strokes, thus increasing efficiency and reducing the time needed for each piece. The press boasts a daylight of 8,000 millimeters, which refers to the maximum distance between the upper and lower press platens when the press is fully open. This substantial daylight is essential for accommodating large workpieces and tooling, enabling the press to handle a wide range of sizes and shapes. Additionally, the distance between the columns, measuring 6,750 millimeters by 2,650 millimeters, provides ample space for maneuvering and positioning workpieces, further enhancing the versatility and functionality of the press. This spacious design is particularly beneficial for forging large and complex parts that require precise positioning and alignment during the forging process.